Okay, evaporation. We've got these three liquids, A, B and C, and we're testing their relative rates of evaporation. So, first question, state control variable other than temperature and volume. Okay, so we're keeping the temperature of all three, well, the initial temperature of all three the same, and the volume of liquid has to be the same. But what else do we have to make sure is constant between all three to make this a fair test? Well, evaporation takes place between where the liquid is in contact with the air, and the greater that area of contact, the more evaporation will take place. So the surface area of all three liquids has to be the same, and that's connected to the shape of the beaker or the container. So you could say that the container of all three has to be the same so that the surface area of all three is the same in order for this to be a fair test. Okay, what do they want next? Give two advantages of using a data logger to measure temperature instead of a thermometer. Two advantages. Okay, well, it takes a reading automatically. It's one thing. You don't have to remove the data logger in order to read it. And what else? Oh yeah, it's more accurate. And yes, using a data logger eliminates the reading error instead of using a thermometer. Don't say human error in this question. They don't accept that as an answer. Use the term reading error. A data logger eliminates reading error from over a thermometer. Okay, next. Calculate the average rate of temperature decrease between 0 and 100 seconds. Okay, they give you this graph which I've attempted to recreate here. Probably not brilliantly accurate, but it'll do. So between 0 and 100 seconds, what do they want? The average rate of temperature decrease for liquid C, isn't it? Yeah, okay. So look at the graph of liquid C on your question sheet, and it wants between 0 and 100 seconds. So go up, okay, and along from 100 seconds. And if you read that off, it's a black line in your question sheet, and that black line crosses at 100 seconds at, I make it 13 degrees C. Okay, that means that in 100 seconds the temperature of C has fallen from 20 degrees C to 13 degrees C. So the difference is 20 minus 13, which is 7 degrees C. So that's a 7 degrees C change per 100 seconds. So divide by 100 seconds. 7 over 100. Yeah, I shouldn't really include the units there. I do apologise. It's 7 over 100. Put the units in at the end, which is 0.07 degrees C per second. Degrees C per second. Okay, so that's the average rate of temperature decrease for C between 0 and 100 seconds. Right, what's next? Give one conclusion about the rate of temperature decrease which all three have in common. Okay, so what they're asking in this question, although I don't think it's expressed brilliantly in the question, they want you to say what all three of these graphs, the rate of all three, have in common. One conclusion that you can say about the rate of A, B and C from this graph that they all have in common. Okay, I've tried to recreate it here, but the one thing they all have in common is that the rate of temperature decrease is greater earlier in the experiment than later on. In other words, the graph is steeper at the start of the experiment than at the end. See, that's steeper for C than there. For B, that's steeper early on than there, and same for A, it's steeper there. In other words, the slant, the slope, is steeper here than here. Okay? That's what all three have in common. Remember, this question is asking about the rate of temperature decrease. It's not asking about the total temperature decrease, because I mean, all three have it, the temperature falls in all three cases. It doesn't go up. That's the only thing that all three have in common as far as the actual temperature decrease goes. But remember, always read the question. They're asking about the rate, and that's the slope. So the answer is that the rate of temperature decrease is greater at the start than at the end. Or we could say that the rate decreases for all three as time goes by. See, if the rate is greater here than here, that means as time goes by, the rate is actually decreasing because the slope is getting less. Okay, enough. What's next? Which had the lowest rate of evaporation, and give reason. The lowest rate of evaporation, that means the one that evaporates the least. Well, when a liquid evaporates, its temperature falls. And we'll get to the reasons why that is in a minute. So, the one with the least evaporation will have the lowest temperature decrease. And that's A. See, A, the temperature has gone down the least for A. So the answer is A, and the reason is what I just said. When a liquid evaporates, its temperature falls. So A has evaporated the least because its temperature has fallen the least. Good. Next. Okay, you did the same experiment again. Keep everything the same, except you have a lower volume of liquid in all three beakers. So instead of to there, you might have the liquid level down to there, maybe. Okay, so that's the only thing you change, and everything else is the same. How would it affect or what effect would it have on the results on this graph example? Well, the answer is no effect. The rate of evaporation of these three liquids, like we've talked about a bit, is dependent upon the temperature and the surface area that the liquid has in contact with the air above it here. If you decrease the volume, so the liquid level is down to where I've drawn it there, the surface area is still the same, the temperature is the same. So this would be the same, your recordings would be the same, doesn't have any effect. Right. Explain how the evaporation of a liquid causes the temperature to decrease. Okay. So, 3 marks. Right. In any liquid, not all the particles, right, so here we are, here is, let's say water, it doesn't matter, any liquid, okay? A liquid is made up of many particles, H2O molecules in the case of water, and they're all jiggling about. Not all of those particles have the same energy. The overall temperature of the liquid might be, I don't know, 20 degrees C, roughly room temperature. But they have a distribution of energy. Some of them are moving slowly because they have a lower energy. Some of them are moving very fast because they have a higher energy. The temperature, the energy of the liquid is determined by the average energy of all the particles. But remember, some are moving slowly, some are moving quickly, and most of them are somewhere in between. So, what's the question again? Explain how evaporation of liquid causes the temperature to decrease. Okay. A liquid evaporates because only a few of these particles have enough energy to evaporate. It's the few that have the high energy. So at the surface here, a particle that happens to have very high energy will be one of the few that has enough energy to escape from the surface, and so that evaporates. Okay, it disappears. It turns into vapor and enters the air as vapor. Okay? Only the high energy particles have enough energy to do that. And so when they've left, they're no longer part of the liquid. And so all the high energy ones, which are constantly evaporating, leaving the surface, if all the high energy ones are leaving, that leaves behind the lower energy ones. And so the average energy of the liquid is decreasing, and therefore the average temperature of the liquid is decreasing. So that's the explanation. What do you actually write in an exam? Well, it's 3 marks. You should say that, keep it fairly concise. In any liquid, the particles all have different energies. 1 mark. Only the most energetic escape, 2 marks. And this lowers the average energy of the remaining particles, 3 marks. Okay, so that's as concise as you could possibly get it in an exam, but it will get you 3 marks. You should probably write a little bit more than that along the lines of the longer explanation I gave, but that's the reasons, the explanation. Okay, well that's the end of the question, but I just want to talk about this a bit more because it's interesting. Have you ever wondered why a liquid can evaporate, why water evaporates and turns into a gas at a temperature much less than its boiling point? If you have some water on the surface in a room at room temperature, 20 degrees C roughly, and you leave it, it will slowly evaporate. But we know that water only turns from a liquid into a gas. You're told that it only turns into a gas at 100 degrees C. That's its boiling point. So evaporation is like boiling in a sense. How is this water boiling at a temperature much less than 20 degrees C? Well, it's for this exact reason. It's because in a water at 20 degrees C, there is a distribution of energies of all the water molecules. A few of them are at a very high energy, and they're the ones that evaporate. And so that's why the water evaporates at a temperature much less than its boiling point. There's this thing called the Maxwell-Boltzmann distribution, which looks like this. If you plot the number of particles against the energy of those particles, then you get a shape, roughly like that, okay? And this is, it's called the Maxwell-Boltzmann distribution. It describes the distribution of particle energies in a liquid, just like we've been talking about. So, the x-axis is the energy of the particles. You you can see that at high energies, this region here, there are not many, but there are some particles here that have a high energy. Most of them are in this sort of mid region here. See, the number of particles is highest in this middle bit. And so most of the particles are around the sort of average energy region. But some, at the very high energy, they're the ones that evaporate and escape. And some are very low down here as well, but they just stay as liquid. And yeah, that explains why liquids at temperatures much less than their boiling point evaporate. You can test it now. Just lick the back of your hand, okay, and blow on it gently. What does it feel like? It's cold, right? And that's how sweating works to cool you. You sweat to make yourself damp, and because of all this, sweat evaporates and takes energy with it, cooling down what's left, you. So the reason it feels cold as you blow on it, the blowing makes the evaporation a bit faster. So if you just lick it and leave it, it still might feel a bit cold, but if you blow on it, it accelerates the evaporation. The reason you feel cold on the back of your hand is because all the fast particles are escaping, they're evaporating, and it's cooling down the liquid that's on your hand, and so it feels cold. Thanks to Maxwell and Boltzmann. Maxwell, Boltzmann. Distribution. Yeah.